So here we're solving an equation that involves more than one trig function. We've got a cos function as well as a sine function within this equation. Now, in order to solve this equation, we will first of all have to get the equation down to something involving either just one trig function or in a factorized form such that each factor has only one trig function. Now, we need to use some of our identities that we know. So we've got sine squared, we've got sine x, and we've got cos squared. So what I'm going to do first of all is I'm going to try and write this cos squared in terms of sine, and then everything will be in terms of sine. So I'll start by writing my trig identity that I'm going to use. So I'm going to use sine squared x plus cos squared x is equal to 1. So that means cos squared x is equal to 1 minus sine squared x. So I'm going to go and substitute this instead of cos squared. So I start by writing 2, and then cos squared x is going to be substituted with 1 minus sine squared x plus my 9 sine x, which is equal to 3 sine squared x is my equation. Expand and tidy this up and equate one side to 0 results in 2 minus 2 sine squared x plus 9 sine x is equal to 3 sine squared x. So this then tidies up to get us 5 sine squared x minus 9 sine x minus 2 is equal to 0. So now we've got a equation which only has sines in it, and we can see it's a quadratic in terms of sine x. So let's go and solve this. So we can let sine x equal to y to make our equation look a bit tidier. So 0 is equal to 5y squared minus 9y minus 2. And so we then need to go and solve this. So I can go and use my function on my calculator, the equation function, to solve this rather than go and factorizing and so forth. So if I go and use my function on the calculator here, I will choose the polynomial function, and a is equal to 5, b is equal to minus 9, and c is equal to minus 2. And when we do that, we get y is equal to 2 as one solution, and we also get y is equal to minus 1 over 5 as my second solution. Go back and substitute y with what it was originally. So sine x is equal to 2, and sine x is equal to minus a fifth. Now, when we try and solve sine x is equal to 2, that gives us an error, and you can check that using your calculator. No solutions here. But sine x equals to minus a fifth when we go and look at this. We should be able to solve that. So x is equal to sine inverse of minus a fifth. And that gets us x is equal to minus 11.5 degrees. And we're not finished here. We need to go and find all the solutions. So here we then draw our sine curve. We'll draw one cycle here for sine. Since we found minus 11.5, I will then add 360 to this to find out the solutions that I've got, or I can actually quite easily draw half of the cycle going backwards, and I'm only going up to there. So what I found is the minus 11.5. Minus 11.5 is somewhere along here, and I need to find any other solutions that I have between minus 180 to positive 180. Now, this one's actually easy to see that from minus 180 to 180, which is just this bit, I only have two solutions, one there and a second one here. So I can find the second one using my properties of symmetry. So How do I find that? Well, it's 11.5 degrees this way, so it's also 11.5 degrees there. So that's minus 180 plus 11.5 degrees will get me my other solution within that cycle from minus 180 to 180. So 180 minus 180 plus 11.5 degrees. And that gets me minus 168.5 degrees. So I will go and write down my solutions. X is equal to minus 11.5, comma, minus 168.5 degrees. And they are all the solutions within that cycle, minus 180 to 180, which we've already considered here using the graph. To solve this trigonometric equation, we can see that we've got two different functions here, sine and cos. So again, we're going to have to go and use one of our trig identities to try and get them down to 1. So we know a trig identity that relates sine and cos as sine theta over cos theta is equal to tan theta. So if I start by writing that equation, 2 sine 2 theta is equal to cos 2 theta, I can divide both sides by cos 2 theta to find an equivalent equation, and right hand side becomes 1, and the left hand side becomes 2 lots of tan 2 theta. Now notice here this identity involves sine theta, but likewise I can do the same thing but with a different angle. Sine 2 theta over cos 2 theta is equal to tan 2 theta, and identities are true for as long as all the angles are the same, the identity is still valid. So now I've got 2 tan 2 theta equals 1. This trig equation only involves one trig function, so we can go ahead and start solving. So tan 2 theta is equal to 1 over 2. And then again, keep the angle intact till the very end. So 2 theta is equal to tan minus 1 of a half. And that gets us 26.6 degrees. Keep this 2 theta intact till the very end. So let's go and find out, first of all the solutions for 2 theta. In order to do this, we need to adjust our interval. Our interval currently is for theta from 0 to 360. So I'm just going to write that down here. Now I'm going to find out what it is for 2 theta, so I need to double my angles, times everything by 2, so 720, and times that by 2 is still 0. So this is the interval that I'm going to be looking for. I'll draw my tan curve here. So tan graph there with an asymptote at 90 degrees and an asymptote at minus 90. Now what I have found is the 26.6 degrees, which is somewhere along here. Okay. Now I've got one solution within the tan cycle, and for the tan cycle we can see here there's only one solution for each value of angle. So if I want to find the next solution, I need to add another 180 to get to the next cycle. So it's relatively straightforward here. So let's go and find out all my other solutions for 2 theta. I'll write down the first one, which is 26.6 degrees. And then to get to the next one, I add another 180. So 180, add the 26.6 degrees, and that gets me 206.6 degrees. I can then get to the next cycle by adding another 180. If I add another 180 to that, I get to 386.6 degrees, which is still within my cycle, as we can see here. Keep on doing that, add another 180, because I want to get all the way up to 720. That gets me 566.6 degrees, which is still fine within 720. Add another 180. And that gets me 746.6 degrees. This one we can see is outside the range, so we stop here. So we found all our solutions for 2 theta. Now we can go and find out what theta is by dividing both sides by 2. So theta is equal to 26.6 divided by 2. That is 13.3 degrees. 206.6 divided by 2. That is 103.3. 386.6 divided by 2. That is 193.3. And 566.6 divided by 2. That is 283.3. So these are my solutions for theta, and we can see that these values are within the original range from 0 to 360 that we have highlighted. Solving this trigonometric equation. If we take a look at this, although there are more than one trig function on this, we don't need to get them all to the same trig function in order to solve this. And this is because what we have here is a factorized form where we have two factors. Here's one factor, and here is our second factor, sine 2x. And in this factorized form, we can see that each factor contains only one trig function. And if you can factorize a trig equation to form factors such that each factor has only one trig function, then it can be solved as well. So how do we go on about solving this? Well, these two factors multiply to give us an answer of 0. Therefore, one of the factors must be 0. So going with the first factor, 1 minus 5 cos 2x could equal to 0. Or we could have sine 2x equaling to 0. So we can then go ahead and solve the first equation that we have here. So we then have cos 2x is equal to 1 over 5. Keep the angle 2x intact till the very end. So 2x is equal to cos inverse of 1/5, and that gives us 78.5 degrees. Now go ahead and find all the other solutions for this interval, which we need to adjust. The interval that we've got for x is from 0 to 180. So let's start by writing down the interval. X is less than or equal to 180, greater than or equal to 0. We need to find the interval for 2x, which is our angle here. So multiply everything by 2, 360, and multiply 0 by 2, still 0. So we need to find all the angles within 0 to 360. So we'll draw the cos graph here. Here's one cycle of the cos graph. That's all we need, one cycle. And we'll look at where 78.5 is. So this is 90, 180. So 78.5 is somewhere around here. Going across, this gives us our second solution, which we can find by using symmetry. So 78.5. So the other solution is going to be 360 minus 78.5, which gives us 281.5. So 2x is equal to 78.5 and 281.5. We can now go and find out what x is by dividing each of those solutions by 2. So we leave the angle intact till the very end after we found all the angles within this new adjusted interval. So x is now equal to, if we divide 2x and 78.5 and 281.5 all by 2, we get x is equal to 78.5 divided by 2, which gives us 39.25. And the second solution is 281.5 divided by 2, and that gets us 140.75. So that's the solution, or part of the solution, we've found the first equation. We then need to go and do the same thing for the second equation, sine 2x is equal to 0. So we said or sine 2x is equal to 0. So let's go and take a look at that. If we solve this, we get 2x, keep the angle intact, is equal to sine inverse of 0. Sine inverse of 0 gives us 0. So we found the solution, one of the solutions. We're going to go and draw the sine curve, and the interval that we're going to look at is still the same thing. It's adjusting the x less than or equal to 180 and greater than 0. So we're still looking at 2x is less than or equal to 360, greater than or equal to 0. So same again, this time drawing the sine curve as we've solved sine. And we have solution 0, and we have 180 and 360. So this one was relatively straightforward. 2x is equal to 0, 180 and 360 for this interval here. Go and find out what x is now by dividing everything by 2. X is equal to 0, 90 and 180. So the complete solutions that we have are here and here. So this was an example of solving, but we didn't need to get it down to the same trig function because in the factorized form, each factor contained only one trig function.